Hello everyone, my name is Raghava Devrajaras. Today's session I'll be talking about my topic video language pre-training based on transformer models. In the pre-training step of machine learning, the model is usually trained on a large amount of data referred to as training data. Once this is complete, it is fine-tuned on a smaller data sets. This step eventually helps in betterment of the downstream task. For natural language processing and computer vision, the transfer-based training has gained a lot of importance. The transformer networks have become popular in the field of deep learning by providing precedence to performance. Having a smaller model bias and network structure easily deepens and makes the transformer ideal for training and fine-tuning. This makes transformers superior compared to multilayer perceptrons, convolution neural networks, or recurrent neural networks. Now, let's see a basic transformer architecture. A standard transformer is made up of several blocks of encoder and decoder. Each block contains several encoders and decoders stacked. The encoder layer is consisting of self-attention or multi-headed attention layers and a feed-forward layer. The decode layer consists of additional encoder-decoder attention layer with self-attention and forward-fast layers. This is one of the core mechanisms, the self-attention, in the transformer that is present in both encoder and decoder blocks. This layer, this linearly transforms the sequence of entirely tokens into three different vectors. The entity tokens can be word sequence in the case of natural language processing and video clips in case of the vision domain. The vectors they used are the key vector, query vector, and value vector. The relevant score between the entities is captured by q into k power t. The reduction of the score is then used for the gradient stability. Softmax normalizes the result of the probability distribution and multiplying the entire value with the vector gives the weighted value matrix. Now, seeing the multi-headed attention, the formula is as shown in the screen. The complex relation between the token entities can be modeled using multi-headed attention. The input sequence X is linearly transformed into H groups, giving each group repeats the self-attention process, projecting the concatenation of the output of H groups with weighted matrix. The process is represented as shown. Now coming to the position encoding, unlike CNN or RNN, self-attention does not have the ability to capture order information of the sequences. This problem is solved by position encoding, which is added to the input encoding of both encoder and decoder blocks. Now getting into the pre-training and fine-tuning aspects, there are two elements. The proxy. Proxy task determines the model learning objectives and hence play an important role in deciding the model performance. The video language downstream task takes care of the downstream task played by a vital role in evaluating the pre-training models. Let's look at them one after the other. Proxy task consists of three elements. It's like completion of the task, matching task, or order task. The completion of task, these are the tasks reconstruct the mask tokens, which provide the ability to build the intra-model or inter-model relationship. In matching tasks, these tasks helps to learn about the alignments between the various modalities originating from the nest sequence prediction of BERT. Ordering task, in the step, the sequence is shuffled, which in turn focuses on the model to recognize the original sequence. The completion of task. These tasks reconstruct the mask tokens, which provide the ability to build the intermodal or intermodal relationship. They have multiple different segments like the MLP, mask language modeling. MLP is the first adapted as the proxy of the pre-training BERT. The common MLP randomly masks the fixed percentage of the words into an input sequence and then helps in predicting the masked words based on other words. In video pre-training, MLM combines the visual information with the generic word occurrence relationships in a sentence. Masked frame modeling, like MLM, MFM, converts sequences into a sentences into a video sequence. The video is continuous entity that has no fixed vocabulary. Hence, in case of MFM, the adjustments made to the input can be subdivided into MFR, that is the MFM with regression, or MFMC, that is mass frame modeling with cross entropy, or MFMCL, that is mass frame modeling with contrastive learning. We will see these MFM tasks used for the various transformer models in future scenarios. So apart from this, we do have masked token modeling, modal modeling, language reconstruction, video language matching, sequence order modeling, and frame order modeling. The video language modeling, the VLM, helps the model to learn by understanding the connection between the video and languages. VLM can be subdivided into LVM, that is local video language matching, and GVLM, that is global video language matching. Frame ordering modeling shuffles the frames randomly and tries to predict the original order. These are all the different completion tasks that we have. Now, getting into the video language downstream tasks, it has a different task like test-based video retrieval. So for a given input, this model retrieves the relevant video or video segments. This approach requires a model to map the video to the text. The action recognition, this classifies the action category of the given video into different video segments. The action segmentation, it's about predicting the action label for the task of the video as any given input. The step localization in this method focuses on recognizing the action steps in a given instructional video. The video questioning answering in this method tries to automate the answers using the natural language questions. Last but not least, the video captioning. For a given video, this method generates the natural language utterances. For a multimodal, this is one of the typical tasks, and the video language pre-training is evaluated using this method. Video language datasets, right? Contrary to the CNNs, the frameworks based on the transformers depend heavily on huge datasets for pre-training. The quality and quantity of the dataset ultimately decide the performance of the model. Commonly used types of datasets are the label-based or caption-based. Label-based, these are the datasets, they have the labels at the video level. Caption-based, these have the datasets which has the description. The captions is based off on the enough information of the corresponding videos. Now, getting into the video language transformer models, there are single stream transformers. There are multiple transformer models that are present, like Video Bird, Hero, Clipbird, uh, Decembird, VLM, VAT. Inside the VAT, there are multiple, like the video audio text transformer or video audio text transformer. So the video bird, it's a first pre-trained model is based off on the transformer, and the combination of the linguistic sentences and the video is known for the input of the training model, which is VideoBird is one of the first to explore the video language representation with a pre-training method based on the transformer. The combination of the linguistic sentence and video tokens in the input of the training of the model is used to learn a combination between the video and text. The correlation is got by predicting the tokens as they are masked. The video word can then learn high-level video representation which captures the long-range temporal dependencies and semantic meaning. It uses MLM, MFM, and VLM in the pre-training phases. HERO stands for Hierarchical Encoder and Omni Representation. HERO uses VLM or FOM proxy task for the sequential nature of the video. Clipboard for the video text representation learning is a generic framework that is used for training the model end to end. Clipboard uses the 2D CNNs to sample a few frames every video clip. And from the memory, as it uses the lower memory, it gives a better performance. Clipboard uses MLM and VLM in the pre-training phases. SMBERT, it stands for dense caption and entropy minimization. The caption generated automatically during the pre-training phase has a lot of noise and may not coincide with the concept of the video. This approach uses the captions as an additional input while the model is learned. The proposed solution from tries to match the captions from the video by using the contained attention loss, which in turn helps the model to select the best matching caption from the pool of candidates. VLM is the video language model BERT. The masked modality is reconstructed by the encoder based on the masked modality. On the other hand, it uses the MTM randomly masked the fixed token and utilizes the loss from the MLM and MVM. VAD is the video audit text transformer. This approach is used for the large-scale self-supervised model with the pure attention model for the end-to-end training. Victor is the video language contrastive multimodal pre-training used for Chinese video language datasets. It uses different network symmetry called key network, which is used for embedded negative sample. And it again used for calculating contrasted losses. Now getting into the mainstream transformers, we have something like CBT, ACBERT, or UniVL. CBT is based off on the BERT structure, which has a multi-stem structure and verifies the loss of effectiveness for cross-modal features. Using the contrastive learning, text transformer and visual transformer learns the text and video features respectively, while the third cross-modal transformer combines the model sequence and computes a similarity score between the video and text. This model has three main components, that is the text transformer, visual transformer, or cross-modal transformer. ACBERT is a multi-stem model which has transformer blocks used for enhancing the communication between the sources. This uses a co-attention transformer layer where key value pairs are passed between the modalities. For the pre-training, it uses MLM, MAM, VLM, etc. The WinVL, this is the one-of-a-kind model which pre-trains the model on understanding and generative proxy tasks. It's made up of two single transformer encoder which embeds the text and video, or one cross-modal transformer which interacts with the text and video embedding, and the other decoder for the generative task. For pre-training, UniVL uses VLM, MFM, MLM, and LR. The downstream tasks include text-based video retrieval, multimodal video captioning, action augmentation, and multi-sentiment analysis. Coming to summarize this, for the transformer block perspective, in case of VATT, the cell attention layer are distributed across modalities while keeping the tokenization and linear projection independent, while VLM has different attention masks, which helps on the downstream tasks for different modalities. ACBERT builds a relation between the various modalities across the independent transformer blocks using the Tangle's transformer block. All the other models discussed in the article uses different original transformer structure like VATT, VLM, ACBERT from the original structure. Coming to the word and video embedding, Victor uses 2D backbone for the Inception 4, which extracts visual features using ImageNet, while Hero combines the 2D features and 3D features. On other hand, VAT and Clipboards have end-to-end frameworks without any fixed visual backbone. The model training objectives can be described by the way of the proxy tasks are designed. These order tasks are good for the tasks that depend on the temporal reasoning. The VLM and UniVL show that rebuilding the modalities helps in retrieval tasks. Finally, the standard approach to evaluate pre-training models is by transferring the pre-trained weight to the downstream tasks. For the retrieval and captioning tasks, VLM has the best practices performance from the single stream model perspective. The UniVL performs the best among all the other multi-stream models that we have seen. Thank you.